Hubel and Wiesel, where they presented the architecture of visual cortex. So they found out that the human perception system is made up of simple and complex cells, and the simple cells basically detect local features, and what the complex cells do is then they pool these local features to build more sophisticated objects, and basically these more sophisticated objects then lead to recognition. So this is also uh, how our visual system works. And now, for a long time, people were trying to basically replicate something similar, not exactly copy, but take inspiration from the human visual cortex and do something similar for machines. And just to give you an example, like basically what a CNN actually does is that it does something very similar to the human visual cortex. So when you have an image, there'll be layers, the initial layers, they'll be responsible for identifying low-level features. And these low-level features, you can see them in the image on the left-hand side. So there are different kind of edges, there are different colors, they are very, very basic shapes, as you can say that, right? You can see a line in between a divide of certain kind. So very basic shapes, or basically lines and some connection of dots or something like that. So the initial layer of a CNN identifies low-level features. It's something very similar to what happens to the in the human visual cortex with the simple cells. And then basically there comes the middle layers. The middle layers basically take these low-level features and they pool them to slightly bigger shapes. Here you can see that the lines are now becoming edges, they're becoming circles and other kind of shapes. And then the next layers of the network will take these middle level features and basically then they will pull them into even bigger shapes and parts. And then basically on these parts, you train a classifier to identify the object in the image. So in many ways, the convolutional neural networks um, perform in a similar way as the human visual cortex. And this is, of course, not my work. This is from Zieler and Ferguson from 2013. Okay, so, and also convolutional neural networks is not a new concept. The convolutional neural networks were proposed in 1980s by Jan LeCun, and at that point, they use convolutional neural networks for digit recognition. And already in the late 1990s, convolutional neural networks were used commercially, especially in banks to read checks. So that was one of the first applications of convolutional neural network in banks and in post offices. So when you would send in a letter, already in 1990s, there were systems that could read the sender's address to the receiver's address and other information that was on the check or a post. Okay, but the real breakthrough, in many sense, happened in 2012 when um, this particular model called AlexNet won the ImageNet challenge. So ImageNet challenge it's one of the largest image data sets. Not now, but at least in 2012, it was definitely the largest uh, data set of images. And the idea was to have a very high performance on this particular data set. So before AlexNet came, people were trying the conventional vision pipelines. Basically, you would have handcrafted features. So you would have a similar idea as convolutions, but those convolution filters would be handcrafted instead of learned from the data. And then came this AlexNet, and they said they were working on this convolutional neural network architecture, and they say, okay, we have a very large, a very deep architecture. Why don't we train it on this very, very large data set? And they did that, and they were very successful with it. So they were able to um, beat the other beat the second place category, the second place participants by a margin of more than 10% point. So there was a large gap in the performance of AlexNet as compared to the conventional pipelines. And with that, the field of convolutional neural networks really exploded. So CVPR, which is the premier conference in computer vision had very little papers on CNNs up till that point, and I think after that it's mostly um, CNNs from then on. Okay, and like people have suggested many different kind of architectures in the last years. In 2013, the VGG network became popular, and then ResNet, DenseNet, and these are just very limited number of examples. So there are many different examples, many different kind of networks that are being used for different kind of tasks. So now coming on the just a second. Yeah. So in the last years, the accuracy of these networks have also uh, increased tremendously. And now in the ImageNet challenge, so you can see where LXNet is on the bottom left, on the red dot on the bottom left, and it was just at around 60%. And now already we have neural networks that can perform uh, that have more than 80% accuracy on the ImageNet challenge. So the accuracy as well as the size of the networks have increased tremendously over the years. And to give you a example of the progress, basically in 2012, AlexNet could only say, okay, this image is of a person or of a dog or a cat. And of course, it didn't have idea. It could not identify multiple objects in the image and so on. And then already in 2015, there were models that were able to segment individual classes in an image. So they could segment a person, a dog, a fridge, bowl, and so on. And by 2017, with Mascar CNN and other models, uh, the accuracy had increased tremendously, and basically it was already nearing human level at that point. So the first task is basically classification. So you have an image, and you're classifying the main class in the image. So in this case, you can say it's a person. And the second task that you see here is called segmentation. And the idea is that you're not just saying the class, which class is there, but you basically select the pixels of the particular class. And of course, they can be multiple classes in the same image. So then you highlight or you select every class. And so this is called segmentation. And then there's also basically object detection, which goes even beyond segmentation, in the sense that you don't say that this is a class A or B. You say this is object one of class A or object two of class A, and so on. So you go beyond the idea of classes, but onto the specific objects. Okay, so this is a bit of a general thing that has happened in the machine learning domain. And now coming back to what I'm doing. So in a recent project, we use convolutional neural networks to detect trees at a very large scale. So we analyzed 1.3 billion, 3 million square kilometer area, and we identified more than 1.8 billion trees in this particular area. So we did a study in Northern Africa, and the rainfall in the area that we studied varied from 0 to 1000 millimeter. So just to give you a motivation of why we are doing this kind of a study, when we are talking about these kind of arid areas and semi-arid areas with very low rainfall, often we know very little about the trees in this area. So when the global tree cover maps are created, these trees are often left out. So if you look at a existing or like state-of-the-art global cover map, tree cover map, it will show that in these areas there are no trees. But that's not true. These areas contain many isolated trees. And isolated trees means that they don't grow as a dense forest, but they grow at some distance. And usually, because of the large distance between them, they're not counted in tree cover maps. So here's uh, a image from one such village in this area, in the area of our study. Okay, you can see um, the red the red square or red rectangle shows the area that we studied in this particular case. It stretched from like deep Sahara to uh, the rainforest in Congo. And basically we had access to very high resolution satellite imagery, uh, because I'm working with NASA, and they had through them we had access to very high resolution satellite imagery, and in particular we had access to two channels, panchromatic and NDVI. So panchromatic is basically a sum of all other satellite channels. So satellites usually have cameras with multiple channels going beyond the normal RGB. So they would also detect uh, near infrared and some other spectral bands. And the panchromatic is just a sum of all the other spectral bands. And other band that we were using was NDVI. So NDVI is the normalized difference vegetation index. It's an artificial band. It's not a natural frequency in the light spectrum, but artificial band. And basically, the idea here is that so it was developed artificially to detect trees from space. So that was the original application of it. And here, the idea is that the trees, they absorb red, so they look green, and they emit near infrared because they're living objects. So it's basically near infrared minus red divided by near infrared plus red. And that gives you high values in places where you have trees and low values where you don't have trees. Or trees could also be like grass or shrub or something basically that's living and it's green. That's essentially the meaning of it. So we had access to very high resolution satellite imagery, and in this particular case, the resolution was 50 centimeter per pixel. Um, 50 centimeter per pixel means that one pixel in the image corresponds to 50 centimeter by 50 centimeter square on the ground. And it's considered a very high resolution imagery that's not easily available, first of all. So there are some sources of open source like image, or basically freely available images, such as the Landsat program of European Union, but there the resolution is 30 meters per pixel. And as compared to that, we had access to very high quality data set. And now the first step when you do a machine learning project is, of course, to get a good quality training data set. So basically the human labels. So this is what we did. We hired some of our team members, basically annotated trees in the satellite image. So they would manually select where a tree is in the satellite image. And you can see how the trees would look like in the image on the right hand side. And now our goal was to like basically take this satellite image and train a model that could uh, basically do what the humans did, what the human annotators had done. So replicate those things. So that is why it's called supervised learning, because it's trying to replicate something. So in this case, it's trying to replicate where the trees are. So humans had annotated it, and then the model is learning to do exactly the same thing. And in this particular case, we used a unit model, or basically a derivative of the unit, not the original version, but a derivative of it with some modifications. And unit has this nice property that you have two paths through which the information flows. One is the U part essentially, and one is the horizontal part. So the information is flowing both vertically and horizontally. So you basically first downscale and then you upscale, and in parallel you pass information horizontally. And basically what this allows is that um, when you have a segmentation task, often the problem is that the uh, localization becomes difficult. So model can detect that there's a cat or a dog in the image, but exactly pinpointing where a cat or a dog is, that becomes a challenging task, because this information is lost when you downsample the image, which is often needed to do these kind of operations. So unit has this nice characteristics that information is flowing both horizontally and vertically. So from the initial layers, you have information about the position, essentially, and then you have um, information about the classes from this deeper part. And that works very nicely. And just to tell you a bit more about the training data that we had created, we had 400 training areas where we had manually annotated trees, and they were spread out in this particular region. Here you can also see other features that are relevant in this particular area, such as farmland and rainfall isohyds. So when you have input data, basically what you try to do is you try to create as much training data as possible from it. So you do a lot of augmentation on the training data. So some kind of augmentation that we used was Gaussian noise, contrast sharpening, and perspective change, and flip, and crop or pad. So these kind of augmentation basically help you to get more out of your small data sets. So in total, we had seven in 90,000 trees manually annotated in this training area. And one particular thing that we asked the annotators was that two conditions must be fulfilled for a thing to be labeled as a tree. So first is the NDVI value should be clearly high. As I told you already, NDVI was originally used to detect trees from space. So it's a very nice indicator whether something is likely to be a tree or not. And the second thing was that a shadow should be seen. And the reason why we went for the second rule was that in this particular area, there are many different kinds of bushes and grasses that grow. And one particular type is the tiger bush that you can see here. And um, from space, they resemble a tree quite a lot. They can get really big sometimes, and then it's very hard to identify whether it's a tree or a bush. And basically, our solution to this was that we asked the annotator to check for a shadow in the panchromatic. So if there was no shadow, the human labeler would not mark it as a tree. Okay, so we trained two models now. One model was only for the desert part, and the other model covered the whole study area. The reason we did that was in the desert, the number of trees is very less um, as compared to the whole study area. So if we had uh, if we had a model only for Sahara, we were able to achieve very high accuracy in this area. So our models achieved 96% accuracy and 99% accuracy for the two areas, and 79% true positive rate and 69% true positive rate, respectively. We also did a lot of validation to make sure that what we are doing makes sense and our results are correct. So we had a totally separate test set. It had nothing to do with the training set that we had used. It was a totally separate set that we had created independently. So those uh, there we had 100 rectangles, and those rectangles were randomly distributed over the whole study area. And in those rectangles, basically, we then uh, in those areas we predicted using our models, and we had a very high correlation with the prediction with the human annotation. So the prediction of our models had very high correlation with the human annotation. But that was not it. We also did some field studies in this area in the past, and we also compared the prediction of our models with what people on the field had observed. So if people would go on the fields and then basically measure diameters of trees and note their position, and we then compare this data with what our model predicts, and we have found very high correlation with our model. So this is correlation is not the same as pixel accuracy, but it still gives you a very good idea. Okay, so then you can see like how does the performance looks like. So you pass in the satellite image, and this is what you're expecting in the third column, which is the labels from the humans, and the fourth column shows the prediction from the model, and you can see that it's very close. In some cases, it was actually even better than what the humans had annotated, because the model learned over a very large area, and then it was even able to distinguish sometimes like bushes and trees, which humans had problems with sometimes in some cases. So the model performed very nicely, and for example, you can see here that every single tree is now demarcated and nicely segmented. So we took this two-step process. Basically, the idea was that we first segment trees in the image, and then we use those segmentation masks to get other properties. For example, how big is the tree and where exactly is the crown, and so on. So we had this two-step process. So first we segmented, and then we calculated the crown shape and those kind of things. But it was uh, it was quite accurate, and it varied. Um, it resembled the human intuition very, very well. Okay, so this is basically how it looks in a larger area. It's not the same village that you saw, but probably it's nearby. Okay, now why is this important? Because we did the study at a very large area, so that was the I think that was the primary contribution. There are studies, there are some of the studies, but they're never done at such a large area. And since we are able to study it at this scale, we could see, for example, how does the canopy cover vary with the rainfall. So we had divided our trees into separate classes, and then basically we could see how does those different classes vary across this whole study area, and how does the different kind of soil conditions affect the tree canopy cover, and so on. We could also study the density of basically the number of trees per hectare in this study area, and see how does the density vary with the rainfall. And one of the things we found was that the density was much higher than what previous studies had reported. So we found that the previous studies were missing up to 89% of the woody vegetation in this region, and at least 84% of the tree cover, which is a huge difference. And we were able to quantify like tree density, crown size, and canopy cover as a function of annual rainfall. And we found a clear imprint of the human management with higher frequency of large crown observed in farmland areas. So another important thing is that the relative high density of large trees in proximity to settlements reveal that often assumed overexploitation of dryland woody vegetation by human population cannot be generalized. You cannot make this claim that humans are exploiting natural resources too much. We did not find evidence of it in this study area. So this was a very interesting finding for us. And in the long term, a mapping of individual trees will improve like monitoring, environment assessment, and information driven land use policy. Like we already did it at more than a country scale. So 1.3 million square kilometer is 3 times the size of Germany. And in the future, we can easily do these kind of studies at a continent or even at a global scale. So we can have a map of individual trees worldwide. And basically that will allow us to monitor and access um, them over a very long period of time, so we can see how does climate change or many other factors impact uh, individual trees over a long period. And this will also help policymakers and different shareholders at protecting and restoring these trees in the arid and semi-arid areas in relation to like mitigation degradation, poverty, and climate change. So that's why it was a very impactful study. It is a very impactful study, and it was accepted for publication in Nature. It's still not out in print, but it will be out in print very soon. And I was the one responsible for developing the machine learning models and the whole pipeline for detection of trees in this particular case. But it was a huge tree. It was a huge project, and we had collaborators from University of Copenhagen, University of Toulouse, and NASA who contributed to it. So it was a very large team that worked on this project. Okay, so that's it from my side. I think I may have managed in, yeah, I think I managed on time. So yeah, I'm open for questions.
Hello, sir. I am Udit Sisodia of third year.
Yeah, hi Udit.
Sir, as you said, we can determine the size or shape of the trees. Can we also determine the breed of the trees from this model?
That's a very good question. So yes, we can probably. So in smaller data sets, of course, people have tried it. So I remember this one study from 2017 where they did exactly the same thing. They were trying to identify the species of trees, and that they achieved an accuracy of around 70%. So of course, it was not as high as for just segmenting trees, but detecting species is a very challenging task because many species look quite similar. And yes, there are approaches to do that. However, the problem is that you'd require some information from the ground for these kind of uh, tasks. For example, for a human annotator, also it's very difficult to see which species is it just from the satellite image. You can identify certain species, but not all. So what you would require in this particular case is that information from the ground level on these species, and then use that to train a model. Um,
Sir, you also told you took data from NASA. So what did you do to clean the data for processing?
so basically, the data came from multiple satellites, and in the pre-processing step, which was done at NASA's part, not our part, they basically made sure that there was no cloud cover, that uh, the so basically sometimes you have some disturbances in the environment, such as sand or clouds or those kind of things, and sometimes the quality of the image is just not good for some particular reason. So this was at their end, that the images that we got were of high quality. They didn't have any cloud cover. They didn't have any environmental effects in them.
Sir, for a complex image, we require a complex model, and the model should also have a big input layer also. So what
Mhm.
was the size of the input layer?
We tried many different input sizes. And the final one that we used were 256 cross 256 pixels in two channels, basically NDVI and panchromatic. But that's again a very good question. What should be the correct input size? And there's no thumb of rule there. You have to essentially try different input sizes, and then you know. In our case, basically, what was happening is, in some images, the values in those images would vary too much within an image. So if you would take a very large image, so we could train our models, for example, on 1000 cross 1000 pixel images. But then what was happening was that some values would dominate the whole image.
Yeah.
And then basically the performance of the model decreased because some values are dominating. And we also tried very small patches up to, I think, 64 cross 64 pixels. And then what would happen is that model will start to detect there will be too many false positives, so it will start to see trees where there are none, because the differences are now so small that everything seems like a tree now, because the NDVI values differ uh, in a very small range now.
And
So
last question, sir, what was this? How many layers does the model contain?
Um, so yeah, I can show you again. So basically, um, we use in terms of layer, we use the same model. So it has an input layer, and then you have four convolution parts, or the basically where the image is downsampled, and then you have four upsample part, and then the output layer, which generates the segmentation.
Okay.
So
Thank you,
yes,
sir.
yeah,
Excuse me, sir.
yeah,
Sir, sir, I have a question, sir.
yeah.
Hello,
Sure, go ahead.
sir. As a beginner, sir, what kind of a learning path or a deep learning?
I would recommend start with a good course. So there's a course on convolutional neural networks by Stanford. I think Stanford 231N. It's a very nice course. It gives you a very thorough understanding of convolutional neural networks. In parallel, what you should do is try some things on different platforms such as Kaggle, or some other challenge, some other platform which allows you, which gives you access to a good quality data set as well as compute resources. Once you have those two things, your learning curve will be much better.
Okay, sir.
Yeah.
So, hello, sir.
Hello. Yeah.
Good morning, sir. This is Navika. Sir, a general question which I want to ask: what are the best techniques we can apply to a deep learning model to get performance out of it? You can just share best techniques which you can apply.
Sorry, your voice was breaking up. I could not hear you.
Yeah, I'll repeat my question. Am I audible now?
Somewhat, not very, not
Um,
very clearly, but sure, go ahead.
so my question was, what are the best techniques which we can apply to our deep learning model in order
Mhm.
to get best performance out of it? So it'll be great if you can just share a few of them with us.
So there's no thumb of rule. It depends upon the task at hand. So your architecture that you want to use heavily depends upon the task at hand. If you just want to do classification, probably unit is not the best architecture. Unit works very well for segmentation. But if you want to do object detection, which is different from segmentation, you will go for something like mask RCNN or a feature pyramid network. The class of networks you want to use depends upon the task at hand. And at the moment, we are only talking about image analysis. Then there are tasks such as speech recognition. Then you have the speech generation and text generation and so on. And they use a very different class of models. So recurrent neural networks, LSTMs, GRUs, gated um, recurrent units, and so on. So the model that you choose heavily depends upon the task you have at hand. For example, in our particular case, main challenge was that the class imbalance was quite high. So in many images, you would have absolutely no trees, only
Yes.
background. So to
Mm.
overcome that, we had to use a special kind of a loss function which could deal with the class imbalance. So that was the main challenge for us, for example.
Oh,
So there's no thumb of
okay.
rule. It
Thank you so
depends
much.
a lot on. Sorry.
Yeah, yes, sir. Continue.
No, it's okay. That's it. Yeah.
Thank
Dive
you
deep,
so
and then you will know for yourself what's the best way. There's no other way. I saw that Anushka wanted to say something.
Guys, do you have any more questions?
Excuse me, sir.
Mhm.
Um, I have a doubt. Sir, since your neural network was so big and the database that you were taking was also huge, how long did the computation cycle last?
Uh,
How did you minimize it?
that's a very good question. So it would take us around a week to train our models from end to end on a high-end GPU. So we were only using one GPU at a time. We were not using multiple GPUs, which is the common approach nowadays, actually. But in our case, we only were using one GPU at a time. And that one GPU, it would take us around 4 to 5 days to train our model end to end. Um, Actually, after the second day already, or even after the first day, you'll have like more than 95% accuracy. But to go into this domain of like 99 or above, you would have to train for many days. So I think if I train a base model now from scratch, I can get decent accuracy in a couple of hours. But then to make sure it really goes into this near human accuracy domain, then you need a lot of high quality data and a lot of training cycles.
Okay,
So
sir.
we didn't do much to optimize it. To be frank, we had access to a couple of supercomputers in our university as well as at NASA, so we could easily do our computation without worrying much about optimization. Of course, it was not as if it was the worst code ever. It was a decent amount of code, but we did not put any extra efforts to optimize it.
Thank you, sir. Also, an unrelated question. Why did you choose to go to Germany to continue this? Why not someplace like US? Since I
Uh,
was confusing.
yeah, I think good question. Uh, yeah, the reason I went for higher studies in the first place was because I started working in Samsung, and then I got quite bored in my job, and then I said, okay, I need to do something more fun. So that's why I went for masters. And the reason I went for Germany was Germany education is free. So It's very affordable, and the quality of education is as good as in US. Of course, there's a language barrier, especially outside the university. So in university, everyone would speak English, but not outside. So there's a language barrier to overcome. But quality of education in general is, I think, as good as in any other place in the world, if not better.
Okay, so thanks for the perspective.
Yeah.
Sir, Nitish, I have joined with my sister's account because of that Anushka has written. Sir, my question is that we should focus more on practical aspect of machine learning or deep learning or theoretical aspect.
Okay, so here's my take on it. You need linear algebra to do machine learning. Basically, machine learning is in a way application of linear algebra. So the convolution operators that we are talking about is in in practice is nothing but a matrix multiplication. So the what learning means is like what kind of matrix do you want to use? I'm sure you know about matrix multiplication, right?
Yes, sir. Yes, sir. Sir,
Yeah. So
so I want to ask that whether I should focus more on maths or should I start practicing more on Kaggle and learn side by side maths? Maths
yeah,
interests me, but I also want to code. That's why I'm
right,
asking.
right. I totally understand that. I would recommend. So this is what approach I took. Um, I first went the practical way. So I took um, multiple courses on machine learning. I think I already was taking courses on machine learning in my bachelor, so it was nothing new for me when I redid some of those courses. So I think I took machine learning courses in my bachelor's, then also in master's, and of course during also my PhD I did some. But in parallel, then I always kept myself updated with what was happening. So as I said, the Stanford course on convolution neural network is very good. It gives you a very thorough understanding of things. But at a certain point, you realize you need to go back to the basics to understand some things. So why does a certain operation make sense? And then you're like, okay, I'm missing the linear algebra perspective on it. And then of course you have to go back to linear algebra, but it does not mean that you have to start with Gilbert Sang introduction to linear algebra. What you can also do is you can look at three blue one brown videos which give you a very nice introduction to linear algebra in couple of hours. So those are very, very nice interactive videos on linear algebra. And if you go through them, then you revise your linear algebra in less than a day, and it's almost what you need for machine learning. Um, on the other hand, if you don't have practical experience, or basically if you're not solving a practical problem, then you can lose motivation in some ways. So you need to have a goal in it, and that I want to do this. I want to have a system that can recognize if my door is open or not. Or I need to have a system that knows who is coming in, who's going out, whatnot. Okay. And I need to have a system that can detect cancer. So when you do those kind of challenges on cable, you have that goal. So that is very important. That gives you motivation to learn. And when you learn, you of course realize that there are gaps in your knowledge. And as you continue, you need to fill those gaps. If you don't fill those gaps, then knowledge becomes superficial in many sense, and you don't want that. So you need linear algebra, but go for the motivation first. Know why you're doing this, and then probably you'll
Sir,
have it.
one more question. So you have done this model in PyTorch, TensorFlow, or Keras. In which framework?
So for different projects, I work on the different teams and different kind of frameworks. So I have used this model both in TensorFlow and Keras. In this particular case, we use it in TensorFlow.
Okay, sir.
Yeah. Uh, Also, if you're a beginner, um, TensorFlow and Keras specifically is very easy to start with. It gives you a very high level overview, and you don't need to do much to create a model and to train it. PyTorch requires a bit more efforts to get started with. So the learning curve is slightly higher.
Any more questions?
Hello.
Yeah.
Good morning, sir. I have a question.
Mhm.
Suppose a student is not good in mathematics,
Mhm.
especially in an algebra. So how would that impact or affect this machine learning journey?
So I think even if you're not good in linear algebra, you can definitely start machine learning. What you'll be limited with is like applying what is already available. If you go into this direction that you want to develop something new, you know, which I think 80% of the people will not go in this direction of developing something new, like coming up with the new architecture or coming up with the new loss function or coming up with the new kind of a layer. If you're not going into that direction, you actually don't need that deep understanding of linear algebra. Just to apply, it's good enough to understand what a what a layer is doing, and then basically just use it. So you have um, different kind of architectures available. You can directly use them. You have uh, all the kinds of layers already implemented in Keras. You don't need to do anything on your own. You just like say, okay, this layer, that layer, this layer, and you're done. And well, this depends upon the architecture you're following. If you're using Unit, you will say, okay, I'll have one convolution, then another convolution, and then a max pooling layer, and then an activation layer, and then a convolution, max pooling, activation, and so on. And those layers are pre-implemented in Keras or PyTorch, and you just need to import them. So you can easily start deep learning without having any idea of of linear algebra. However, if you want to go deeper, for example, you come across a problem like the certain loss function is not what you're looking for, and now you want to understand how I can improve a certain loss function, then you would need a stronger background in mathematics.
Thank you, sir.
So I just like to take a minute and thank Ankit sir for delivering such an amazing talk and informative talk. We learned a lot today, sir. Thank you so much.
Yeah, you're welcome.
Vanita ma'am and Sarita ma'am, our faculty members for society who have helped us out, and our core team members who have played.
You're very welcome. Ah, Bhumika,
Different audience.
you didn't play the video from Johannes. Let me do that. Or can you do that? So my professor have a small video for you guys, 1 minute video. So just
Yes, sir, just
let me just play.
so I shared my screen.
Okay. I can play it. I have it on my machine, so maybe I'll just check.
I guess there's some technical issues. So you can share your screen.
Yeah, just see.
Welcome to the University of Bremen. My name is Johannes Schill. Unfortunately, I cannot be here with you today, but it's my pleasure that Ankit will provide a lot about our research group and institution. The University of Bremen in Germany is one of the biggest and most versed universities in North Germany. The university is a very international other as well as international universities with various programs, like, for example, Erasmus. It also has a very close connection with large national and well-known research institutes located directly here on our campus, like the German Aerospace Research Center, DLR, or the DSKI, the German Institute for Research in Artificial Intelligence, that I also got my PhD from. Our university employs over 300 full professors and consists of 12 departments, and we teach about 20,000 students. But that should be enough about our university. I hope you have some fun and learn new insights with the talk Ankit is delivering today. Namaste.
So that was from Johannes. Thank you very much. Yeah, okay, that's it from my side for today.
Thank you, sir.
Yeah, you're welcome. Bye.
Bye, sir.
Bye, sir.
Bye.
Thank you, sir.